All right, now I'm recording the third video for 114. So last time we finished the lecture 12, slide 5, the velocity selector. Okay, so don't be afraid of these fancy names. A velocity selector is nothing but a device where a uniform magnetic field and electric field set up in the same region, so that any particles coming in will feel these two forces, right? And then these two fields, they're set up so these two forces, they're always going to be in opposite directions, right? As we did last time. So if the charge feels two forces in opposite directions, one is an electric force, one is a magnetic force. Okay, we did it last time. So and then the motion of this. So but this charge has a velocity dam. Then the motion of this charge inside this velocity selector is totally determined by these two forces, right? So, but there will be some lucky particles where these two forces are equal, right? And these are the particles we are interested in, okay? So if these two forces are equal, then the net force on these particles is 0. Then this guy feels nothing, right? Feels as if nothing is on it. So this guy is going to keep moving in a straight line with this initial velocity, okay? And then through this velocity selector. And then you can use the expression for the electric force and magnetic force. You will find that in order to pass this velocity selector without any deflection, right? Because if the electric force is larger, it's going to be deflected that way, or if magnetic force is larger, it's going to be deflected this way. But these particles, if they satisfy this condition, right, and then they will pass through this region without any deflection, okay? And then you can rewrite this equation. At the end, you'll find that these particles, they will have a velocity which is just going to be equal to the ratio of these two fields, right? Again, this is not an equation you should remember. Otherwise, you're going to remember a lot of equations in physics, right? But how did we derive this equation? Well, this is the idea, right? We want these particles, some lucky particles, and these are the only particles we're interested in, because we want to select some particles with a certain speed, right? These lucky particles, because these two forces equal on them, so they pass through this region without any deflection. You set them equal. You do the algebra. You will find this, okay? So that's what we do in physics. This is a conclusion, okay? And then, as I said last time, and then if you want to select particles with a certain speed in a real experiment, that's what you do, right? Because you can grab these particles, okay? So say if I want to select the speed of particles with this number, okay, all you need to do is just set up a velocity selector and then tune these two fields and make sure the ratio between them is this number. Then you have all kinds of particles enter this velocity selector. So these particles can be produced by a different experiment. And when you produce particles, usually you have a lot of particles, right? Different kinds of particles, different velocity. You have them all coming in, okay? And then you just wait here and collect particles which can go through this region, right? Because other particles, if they are deflected, you don't get them. And then I'm not interested in these particles. So I only collect the particles after this velocity selector. All these particles, if they have already passed this velocity selector without any deflection, their velocity must be equal to the ratio I set up, right? So that's how we select the particles with a certain speed, right? And you can always tune these two fields. So you can use velocity selector to select particles with any speed you want, okay? So that's one application. So actually, J.J. Thomson, in 1897, he used this idea to discover the electron. Okay, so this image, okay, shows you the on slide 6, lecture 12, slide 6. So this image shows you the device J.J. Thomson used. So first of all, well, he didn't know that that was the electrons he generated in this experiment, right? But what he did was that, so some particles generated in this cathode, okay, and then these particles, they have some speed, they move straight, okay, they reach these two anodes, okay, then they're going to be accelerated between, so this is pretty much like a parallel plate capacitor, right? So there's the electric field here. If there's a charged particle inside this parallel plate, then they will be accelerated, okay? So it's not going to change the direction. It's still going to keep moving in the same direction, but it's going to be accelerated. Then it keeps moving in a straight line. It's going to enter this region. You can see that. So with both magnetic field and electric field in the same region, right? So the electric field is down. These red arrows is the electric field, and the magnetic field is into the page, the blue arrows. So, and then, okay, you can try, you can find these two forces on the electron, assume it's a negative charge. You can try that yourself. And these two forces, they're going to be, again, in opposite directions. Then how do these electrons move in this region? Well, it totally depends on which force is larger, right? So what J.J. Thomson did was that he can change these two fields, right? He can change these two fields, the electric field and magnetic field, because you're going to set up these two fields in this experiment. And then he can find that once he have these two fields with a certain number, so the electrons, they can pass through this region without any deflection. So that means these two forces are equal on this particle. And then they're going to keep going in a straight line until it hits the screen. Okay? So you see that, and then you can do the algebra. Okay? You can first calculate the velocity of these particles after this parallel plate capacitor. Right? Again, you don't need to remember these equations on this slide. Okay? There's no point in doing that. Okay? You will get some problems on the homework to practice this theory, okay? Both electric field and magnetic field. And then after all the algebra, you can find the charge mass ratio of this particle can be calculated using, that's the last equation on this slide. It's going to be calculated by the electric field, magnetic field, and the potential difference between these anodes, right? So these three things, you can control that in the experiment. Actually, you set up the electric field, the magnetic field, and the potential difference between these two anodes, the A and A prime, okay? And then you tune these three numbers until you see these particles hit the screen, okay, without any diffraction. Then you use these numbers, you can calculate charge mass ratio. And he realized that every time he does this experiment, okay, if these particles, they can go straight and then hit the screen, then he calculated the charge mass ratio is always one number. So that means that's one kind of particle. And then he called it an electron. So that's how he discovered electron. Okay? All right, so that's one application of the magnetic force. Okay, another application of the magnetic force is called mass spectrometer. Okay, again, don't be afraid of these fancy names. Okay, a mass spectrometer is nothing but just a uniform magnetic field used to separate particles. Okay, so what does the mass spectrometer do? The mass spectrometer is going to separate particles. So what we usually do is this. Okay. First, as I said, you have a lot of particles, right? In a real experiment, a lot of particles, elementary particles have been produced. Then what we usually do is that you can have them go through a velocity selector. Then you collect the velocity selector, the particles after the velocity selector. So they will have a velocity which is going to be equal to this number, right? So in this region, say we use the velocity selector. Okay, I'm going to redraw this. This diagram is a little bit different than the one. for the velocity selector. So there's the electric field, right? So this is the velocity selector. So both of these two fields are in the same region, right? Magnetic field into the page. Okay, this is still a velocity selector, right? Uniform electric field and magnetic field in the same region. So this is electric field. Magnetic field, we're going to call it B1, because we're going to have another magnetic field. So you have all these particles come into this velocity selector, right? And then some of them are going to, a lot of particles, different velocities, okay? Some of them are going to be deflected to the left, some of them are going to be deflected to the right, right? Because they're going to feel two forces, right? Say a positive particle is going to feel a force, electric force to the, in this case, to the right, and the magnetic to the left. You can use right-hand rule to find the magnetic force, right? And then, but these particles with this speed, some particles, they're going to, because you have these particles in a wide range, with a wide range of velocity, right? Some particles, they will have speed equal to this ratio, right? So this part, then you collect these particles here. So there are a lot of particles, they can pass through this region without any deflection. All these particles, they're going to have the same velocity, right? Now I'm going to call it B1 because I'm going to use another magnetic field after this. So, okay, so these particles, they already have the same speed, but they're still different particles, remember, okay? Because when we set up these two forces, we didn't use any information of the particle itself, right? We set up these two forces equal, and then the charge cancels. We don't even need mass, so at the end, you don't need any information of the particle. As long as they have this speed, they're going to pass through this region without any diffraction. Now you're going to have them enter a mass spectrometer. A mass spectrometer is nothing but just another magnetic field, only magnetic field in this region, right? So say we set up another magnetic field out of the page in this region. So these particles, which have passed through the velocity selector, they already have this velocity, right? So I already removed one variable, right? Because I don't want to have like a lot of particles with different velocity. But there are still different kinds of particles, right? Once they reach this second region, which is only a magnetic field, no electric field, right? Moving charges in magnetic field, how do they move? Circles, right? If you see a moving charge in a magnetic field, only magnetic field, nothing else, or uniform magnetic field, they're going to be moving in circles, right? And then because they're different charges, right? So it totally depends on their charge, their mass, they're going to move in different circles, right? So say some particles, they're going to move in a circle like this. And then there are some other particles, they're going to move in a big circle, all right? And then some particles, because they have different signs, they may move in a circle to the right, okay? So anyway, so different particles, even though they have the same speed as they enter the mass spectrometer, which is nothing but just a uniform magnetic field, okay? They're gonna hit this plate, this detector array, in different detector at different locations, right? And then you can use the different locations to identify these different particles. You can also separate these particles, right? Because they're gonna hit the detector at different locations, right? They come in, you just see a bunch of different particles, but then you set up this uniform magnetic field, and then they're gonna move in a circle, and then they move in different circles, so they will hit the detector at different locations. And then the radius, we can find the radius, because we can always predict the radius of the circular motion of a moving particle, a charged particle in a magnetic field, right? The equation we derived was this. Right? Whenever you see moving charge in the magnetic field, it's always going to be this equation and then this one, right? Again, you need to know how to derive these two equations. You don't need to memorize all these conclusions, all these equations, right? That's not what we're doing in physics. So now you see that, okay, how do I predict the radius of each circle, right? Well, that's going to be this equation, r equals that. Now let's write it down here. So in this region, each particle, so you will have different particles. They will hit the, now it's going to be B2, right? Because they move in the magnetic field in this mass spectrometer. Has nothing to do with this, okay? Now, but you can also measure this radius, right? Because they're going to hit the detector at different locations, right? So at the end, you measure the radius, then you rearrange this equation. You can find the charge mass ratio of each particle. Then you can identify them, right? So how do we do that? They already carry this velocity, right? So you plug it in, then what do you get? You get R equals M E divided by B1 B2, right? And then let's rearrange it a little bit more. So I would get, multiply both sides by this guy, you will get R Q B2 equals M E over B1, right? And then let's put charge and mass together, right? So what do you get? You will get this. Right? So, and then you see that what we want to do in this experiment is actually identify this. Because again, when you do an experiment, a real experiment, you don't know what particles you have generated in this experiment, right? You can't see them, you can only detect them. When you detect them, the detector is not going to take a picture of each particle. Then you compare the picture you get to the picture of different particles, right? You never see like faces of these particles, right? So you have to use some parameters you can measure to identify these particles, right? Now, once you derive this equation, you see all these guys on the right. Okay, they can be measured, right? Electric field, magnetic field, these two magnetic fields, you actually set them up in a real experiment. So you will just have these numbers ready, right? And then what about the radius? Well, that's just going to be the location of the particle in the detector. So you can definitely measure that, right? Well, you measure the diameter, then you divide by 2, right? So all these numbers on the right, you actually can measure them from the experiment. Then you do the math, okay? You can calculate the charge mass ratio of each particle you detect in this experiment. And then the charge mass ratio is like the ID of these elemental particles. So using this, so each elemental particle, proton, electron, helium, silicon, okay, they will have a unique charge mass ratio, right? Some particles, they even have the same charge, but the charge mass ratio is going to be unique for every elemental particle. So that's their ID, right? If you can calculate this number using the parameters that can be measured in an experiment, that's how you identify these particles, all right? So again, there's no point, there's no need to remember this equation, right? This is a conclusion. This is not a general equation that you can remember, just apply to any question whenever you see, oh, charge mass ratio, okay? So don't do that. Our goal is to understand all these process, okay? All right? Now, let's take a look at a problem, slide 8. So let's practice this theory. A mass spectrometer, okay, again, don't be afraid of these fancy names. It's just nothing but a uniform magnetic field used to separate particles. It's being used to separate common oxygen-16 from the much rarer oxygen-18, taken from a sample of gold glacial ice, okay? So it's used to separate 16 from oxygen 18. Okay, how do you separate them? Well, they're going to have different charge mass ratio, right? So first of all, you know the ratio of the masses is going to be 16 to 18, of course. That's why they called 16 and 18, right? So, and then we know the mass of the oxygen 16, and then you can use the ratio to find the mass of the oxygen 18, right? They both carry positive charge E, okay? So they have been charged with one positive charge, okay? And travel at this 5 times 10, 6 meters per second in a 1.2 Tesla magnetic field, okay? What is the separation between their locations when they hit the target after transverse the semicircle, okay? So, okay, you see that, take a look at the image here. So these particles, they're going to be generated from the iron source, right? And then these two different isotopes, they're going to be mixed, right? You can't separate that, okay? You're going to first have them, you see that go through a velocity selector, which is the first region, with both electric field and a magnetic field, right? But you don't need to worry about that because the problem already tells you that, okay, they're going to travel at 5 times 10 to the 6 meters in 1.2 Tesla magnetic field. So that means, okay, we don't need to worry about the velocity selector. After the velocity selector, all these two particles, they carry the same speed, okay? So that's a speed, right? Now, after they have this, passed this velocity selector, they will enter this 1.2 Tesla magnetic field. I want to find separation between their locations when they hit a target. So that's what happens, right? So they hit the they're going to enter, so we don't need to worry about the velocity selector because they already passed the velocity selector. They will have the same speed, 5 times the 10 to the 6 meters per second. Now they enter this mass spectrometer. The mass spectrometer, it's going to be one uniform magnetic field out of the page. Okay, and then you see that. So because they have different charge mass ratio, right? So they're going to move in two different circles, and then, right? So the second one is going to, I don't know which is which, but this is going to be the two circles, right? Now we want to find a difference between their their locations after they transfer the semicircle. So basically, we just need to know this little distance, okay? And what is the little distance? Well, it's just the difference between these two diameters, right? You see that once you know what this problem says, you know what to do, right? Otherwise, you look at this story, you read this story, you don't even know what it's saying, right? So many fancy words, so many scary terms, okay? So actually, the problem just says, just find the difference between these two diameters. How do I find the difference between these two diameters? Well, we have the equation for the radius. That's what we derived, right? So whenever there's a moving charge in a uniform magnetic field, they always move in circles. The radius always calculated this way. Now, if you want me to find this d, that's just going to be the difference between these two diameters, right? Which is just going to be 2 times the radius. Okay, I'm going to use the absolute sign because I don't know which one is larger, which one is smaller, right? So I don't even need to figure out which one minus which one. Okay, just put an absolute sign there. Now, okay, how do I find these two radii? Well, I use that equation. So I can even pull out these two. Okay, so that's going to be M16 VQB minus M18 VQB. Right. The masses are different. What about the 3 other guys? So V, the problem already tells you they will carry the same V, okay? So the V is going to be different. I don't need to plug 2 different numbers. But again, it's only true for this case, right? Now the chart, the problem also says they both carry positive charge E. So they both carry one positive charge E, okay? So this guy is going to be E, right? And the magnetic field is also the same, right? Because they are in the same magnetic field. And this is 1.2 Tesla. Okay, so that means I can even pull out these three guys. The charge is going to be E, positive E. In this case, right, it's not always E, okay? The problem tells you that they both carry positive charge E, okay? Sometimes they carry 2E, 3E, or negative 4E, right? Okay, you pull out this factor out of V charge and B, then you only need to calculate this. Again, let's put the absolute value here. Okay, so that's very easy. Okay, so the velocity is given. This is the velocity plugging. The magnetic field is this number, right? The little e is a constant, right? What about these two masses? The problem says the mass of this oxygen 16 is this. Then you can find the mass of the oxygen 18, right? Because the ratio between these two masses is 16 to 18, right? So the ratio between these two numbers is going to be 18 over 16, right? So the M18 is going to be M16 times this ratio. Okay, now you see you do have all the numbers you need, right? Just plug them into this equation, and then you can find the separation between the locations when they hit this target after transfers. It's so simple. Okay, try that. See if you can get the right answer. Okay, so now let's do that. Okay, so this E is right. So you will have all these numbers. This M18 you can find is going to be 2.99 times 10 to the negative 20. Okay, so just put these numbers in, and then obviously M18 is going to be larger than M16, right? Okay, but use the absolute value so you make sure you get all the positive number. Okay, so that's going to be different. And you see that this difference is like 17 centimeters. So it's very easy to measure in a real experiment, right? So that's how we separate these two particles in a real experiment. All right, so we have finished lecture 12. Now we're going to move on to lecture 13. Okay, so magnetic force on a current carrying conductor. Okay, so because we learned that, now I'm going to erase all this. Okay. The magnetic field had a force on a moving charge, right? Always. So, but if there are two charges, both of them are going to feel the force from the magnetic field. If there's a medium charges, each of them is going to feel magnetic force from the magnetic field, right? What if there's a current, right? A current is nothing but a lot of electric charges flowing in a conductor, right? So that means each charge is going to feel a magnetic force. So that means if you add all these forces together, you will get a net force on this conductor, right? So say if I draw a conductor, like a straight, long straight conductor, okay, so the current is going this way. So all the positive charges, they're moving to the right, right? Because the direction of the current is the direction of the moving positive charges. And then, okay, there are like millions of charges moving in this conductor. Each charge is going to feel force from the magnetic field. Like say, if I place this charge in the magnetic field out of the page, into the page, okay? Each charge is going to feel force from the magnetic field, right? What is the direction of each force? This guy, you're going to do V toward B, and this is a positive charge, so the force is going to be up, right? So this guy is going to feel force up. And what about this guy? Well, it's the same, right? It's moving in the same direction, magnetic field in the same direction. it's also going to feel a force up. So every little charge, if this is a straight conductor, every little charge is going to feel a force in the same direction. So that means at the end, you add all these forces together, right? And because they are in the same direction, you can just add these numbers, right? At the end, you will see there's a net force on this conductor, right? Which is just going to be the sum of all these little forces, okay? Then how do I find this total force on the conductor? Well, in principle, you should do this for every little particle, and then you add them together. But that's going to be a lot of work, right? First of all, there are like millions of a charged particle here, okay? So you're going to do like, have more than a million numbers, add them together, right? So we don't need to do that, okay? Fortunately, you do some math, okay? That's what I usually say. Math makes things easier. Math doesn't make things hard, okay? But you have to get used to this new language, right? You do some algebra, okay? So basically, the net force on this conductor, it's going to be all these little forces, right, on each charge. So you're going to add all these guys together. Okay? You do some math. We're not going to show it here, okay? And then at the end, you don't actually need to do this summation. You can just do this. Use the current and the length of this conductor, and then the magnetic field. You use these three numbers to find out the net force on the conductor. Okay, and the current is something you can measure. A length is very easy to measure in, right? And magnetic field, it's going to be set up, right? So that's also a number you can measure. Okay. So that's going to be the equation we use to find out the magnetic force on a current carrying a conductor. Okay? But this is nothing but a conclusion from this theory. Okay? So it's because the magnetic field has a force on every single charge. You add all these forces together, you will get this equation. Okay, we're going to list it as a new equation, but this is only a conclusion from this theory. Okay, this is not a new theory, but when you want to find the force on a carrying conductor, this is easier to use than that, right? So we're going to list it as a new equation, but it's not a new law. Okay. All right, so this equation is also going to be given on the test, right? Because we didn't derive that. So how do I use that equation? You still see a cross product here, right? So that means when you find the magnitude of this force, you're going to still do this. I, L, B, sine theta. With which this theta angle is going to be the angle between these two vectors. Okay, B is a vector. I can understand that. B is the magnetic field, right? The field vector has a direction. The L is a length. How come a length has a direction? Well, a length doesn't have a direction, okay? But in order to make a vector here, and then also we want to make a cross product here. So we have to make some vector to cross it into this B, okay? So that's why we make this guy a vector, okay? Then what is going to be the definition of the direction of this L? It's just the direction of I, okay? So you could just say, let's make this I a vector, right? You just write this way. Either way, right? You can make any definition you like in physics, right? But this makes more sense. Well, I shouldn't say it makes more sense, right? People are more used to this than this, because if you say current is a vector, well, that's even stranger, okay? So that's why this is going to be the notation we use, okay? We do I, L crosses B, okay? We consider the length also as a vector, but the magnitude is just going to be the length, the number in meters. The direction is going to be the direction of the current. So actually, when you do, right, so magnitude easy. Just calculate this, find these four numbers, multiply them together, right? And the theta angle is going to be the angle between these two vectors, which is actually the angle between the current and the magnetic field, right? Remember, we defined the direction of this length vector to be the direction of the current. So in this case, the L is going to be in that direction. Okay. Now, then what is the direction? Well, the direction, you're still going to do L crosses B, so you're going to, like that equation, right? This is still a cross product. You're going to put your forefingers in the direction of the first vector, which is L. But the direction, what is the direction of the L? It's I, right? So basically, you're going to put your forefingers in the direction of the current and curl them into the direction of B. So you do I toward B, then your thumb is the direction of force. And in this case, it's even easier than that equation because there's no negative current, right? So the current is always positive, flowing. So you don't need to flip your thumb. Once you do I toward B, then your thumb is the direction of the force, right? So in this case, for example, if I don't use that, right, I don't need to worry about the force on each charge. So if I just want to use this equation, the current is going that way, the magnetic field into the page, so I would just do I toward B. So this whole conductor is going to feel net force up. Okay? So that's the magnetic force on a current carrying conductor. Okay? All right, so that's how we use this law, right? The slide 2 explains how we find the magnitude and the direction. The magnitude, you just multiply these numbers together. This is how you do cross product, right? And the direction, still right-hand rule. Now we're doing I toward B, but it's essentially the same as V toward B, right? Because the direction of the I is just the direction of this moving positive charge. So it's just got the direction of the V of each positive charge, right? So you're still doing V toward B, but now the V and I are in the same direction, and I is easier to see, so we just do I toward B, okay? So still right-hand rule, and then you don't really need to flip your thumb in this case, because current is always positive, all right? Okay, so now let's take a look at slide 3, a question. So we're going to practice this new theory we learned on current carrying conductor. All right, so a loop of wire carrying current. This number is placed in a uniform magnetic field. Okay, with this number, the plane of the loop is perpendicular to the field. So, okay, it gives you the length of the bottom and the left and right sides inside the magnetic field. We want to find the magnitude and direction of the net magnetic force on the loop. Okay, so let's draw it out. So it's very interesting. The magnetic field is only inside this circular region and is out of the page, uniform. There's a magnetic field coming out, okay. Now there's a loop of wire placed in here, okay. So only this part is inside the magnetic field, right? So it might be connected to something else or a battery, but it doesn't matter, we don't care, right? Because it's only going to feel force. Only this part is going to feel force, because only this part is inside the magnetic field. So the direction of the current is going counterclockwise. Right. We want to find the magnitude and direction of the net magnetic force on the loop. Okay, how do we find the magnetic force on this loop? We never learned how to find the magnetic force on the loop. Well, you see this portion is just made of 3 straight wires, right? So all you need to do is just find the magnetic force on each wire, each straight segment, and then add them as vectors. Again, add them as vectors, because force is a vector, right? You just don't add, I find 3 numbers, I add them together, okay? You need to take a look at that direction, all right? So let's do that. So first of all, let's figure out the direction of these 3 forces, and then we can do the algebra, right? This guy, okay, so you're going to do I toward B, right? So B is out, so what do you do, okay? Use the right hand, put your forefinger in the direction of I, down, and then you're going to curl them into the direction of B, which is out of the page in this case. So you're going to do it this way, actually. Right, I toward B. So your thumb is to the left. So this force is actually to the left. So let's call it F1. So this segment is going to feel a force to the left. What about this segment, the bottom one? The bottom one, you're going to still do I toward B, right? So this is a little bit hard to do. You're going to do I toward B because B is going to be out, right? I toward B. So thumb is down. So let's call this F2. Now what about this guy? This segment, current is up, magnetic field is out of the page, I toward B, I toward B. So this guy is going to feel a force in that direction. So basically you're going to add these three vectors together. So you're going to do X and Y, right? In principle. These two guys, they are in X direction. You can add them with the correct signs. This one is in Y direction. And this is the only component in Y direction. And once you have X and Y components, you're going to combine them, do trick to find the magnitude and direction. But in this case, it's a little bit easier, okay? But that's what you should do, right, in principle. Because if you find F1, F3, so let's do this. So let's find an expression for F1 and F3. Saying you F1 is going to be ILB sine theta. So let's do that. It's going to be the same I, so I don't need a subscript, right? L1, so which is the length of this side. Okay, so this is L1. B is going to be the same, right? Because it's the same magnetic field. Now the sine theta angle. So what is the angle between the I and B, right? I is down, B is out of the page. Okay, 90 degrees. This is a simple case. But again, it's not always 90. Okay, a lot of people, they always remember this special conclusion, the simplest case, they apply that to all the questions they see. No, okay? You just use the definition to find every number carefully, then multiply them. So this is the F1, right? And this force is to the left, right? Now F3, it's going to be I, L3, B, sine, what is this angle? I is up, magnetic field is out, so that's still 90. And this force is to the right. And then F2, it's going to be I, L2, B, sine. What is the angle between them? I to the right, B out of the page, so still 90. And this force is down. Okay, so you're going to add all these three forces together, X and Y components, right? But this problem is easy because these two X components, they're going to cancel each other, right? L1, the only difference between these two expressions is going to be the length, but L1 and L3, they're the same, right? Because of this symmetry. So these two guys, they're going to actually cancel out exactly. Okay, so this is an easy question. So the net force, right, you should do F1 plus F2 plus F3 as vectors, right? Then you break them into X and Y, add X components together, add Y components. But in this case, it's easy because F1 and F3, you add them together, these two vectors together, you get just 0. So the net force is just going to be F2. Right? And the F2 is this expression. So now you can put numbers in. So you only need actually the length of the bottom side, right? Which is 20 centimeters. So L2 is 12 meters. Right? Then you know the current, you know the magnetic field, and sine 90, you can plug all the numbers in. Okay? So you don't even need the 45 length because these two numbers, they're going to cancel out in opposite direction. All right, you can find out. This is a value, direction is down. Okay, but you will see some problems on the homework with different angles with X and Y components. Then you will do trick, but it's the same idea. Okay. This theory is new, but once you find these three vectors, you're still doing vector analysis. That's still what we learn in Physics 1. We're still using the skills and the theories we learned in Physics 1. Okay. All right, so this is this question. Now let's take a look at the next question, slide 4, lecture 13. Okay. A conducting bar of this length and this mass rests at the left end of two rails of this length. Okay. There's a magnetic field pointing upward. Okay. So in which direction will current through the conducting bar cause the bar to experience a force to the right? Okay, now we again doing things backwards. We don't know the direction of the current in this bar, but we know that at the end the bar is going to move to the right. Okay, it's going to feel a force from the magnetic field to the right. It's going to move to the right. What is the direction of the current in the bar? Okay, so let's erase. I'm going to erase this. All right, so it's easier to draw a top view, right? You're looking at this thing from the top. What do you see? You actually see these two rails like this, and then there's a bar here. So this bar has its current, right? And then the magnetic field is pointing upward. But if you look from the top, so you see the magnetic field coming out, right? So you will see dots out of the page. So that's a view from the top, right? Okay, so you have the magnetic field out of the page. You don't know the direction of the current. You want to find the direction of the current so that it feels a force. At the end, it's going to feel a force to the right, magnetic force. So what would be the direction of the current in this bar? Okay, think about it. Okay, first of all, there are only two options of the current, right? The current can go either up or down, right? Because say this guy is connected to a battery or something. So the current is going to be either up and down. There's no, you can't have a current in this guy like left or right, right? So is it going to be up and down? So again, you're going to do things backwards. So how do you use right-hand rule to determine the force? You're going to put your four fingers in the direction of the current, which you don't know here, right? So that means you're going to try, okay? And then curl them into the direction of B, so your thumb is the direction of force. So now I know that at the end I will point my thumb in that direction, and then I would curl my four fingers out of the page in this direction. So how would I put my four fingers in the first place so that I would have my thumb in that direction? Okay, try that. Okay, see if you can get the direction. So the right way to do that is this, right? If you put your four fingers up and curl them out of the page toward yourself, you see now your thumb is to the right. So that means the current in this bar actually should be going up. Okay, so it may be connected to a battery like this, right? Okay, and then the current is going up. Okay, so that's this. So it's going to be up in the bar. Okay. Now, what about the second part, slide 5? If the rails are frictionless, we want to find the bar speed and leave the rails at the right end. Okay, so there's no friction. This guy's moving only under this force, right? On this plane, there's still gravity and normal force, right? Gravity is in that direction. Normal force is now in this direction because this is the top view, okay? But these two forces are going to cancel in y direction. So it only feels a force in x direction in that direction. So it's going to be accelerating. That's still Newton's laws, right? Newton's second law. Constant force, constant acceleration. So it's going to be moving in that direction and faster. We just want to find the velocity of this bar when it reaches this end, okay? So then you see that this is a constant force, constant acceleration motion, right? If I want to draw write an equivalent problem in mechanics, is going to be this, right? Something feels a pulling force to the right. Now it's a magnetic force, but it's just a force. A force is pulling this thing to the right, no friction. and then find the final speed of this guy after some distance, right? We know how to solve this problem, right? You can either do kinematics or conservation of energy, right? Okay, so try that. Either you can use conservation of energy or kinematics. You can find the force, you can find the velocity of this guy at this point, okay? So if you want to use, let's see, we know the length of this, oh, it's going to move a distance. So this is a distance. The length is this side. This is the d. So that's the distance you're going to travel, right? So let's move it to this problem, mechanics problem, okay? It's going to travel this distance. How do you find the final speed if it starts from rest? If you want to use kinematics, right? So the easiest way is to pick the third equation, right? Vxf squared equals Vxi squared plus 2ax xf minus xi. This is going to be the distance you plug in, right? Initial velocity is 0. You're looking for final velocity. The only thing you need is going to be acceleration. How do you find acceleration? You're going to do Newton's second law, right? So the acceleration in x direction is going to be the net force in x direction divided the mass. Right, the mass is given. Then you need to find the net force. But the net force in x direction is just going to be the magnetic force. Right? How do you find the magnetic force? That's when you use this new theory. Right? So that's the only place you use this new theory. Other than that, this is what we learned in physics 1. Kinematic equations, Newton's second law. So how do you find the magnetic force? I, it's given. L, now this is the L you use, right? The length of the bar, not this. This is the rails, has nothing to do with this guy. B is given. What is angle theta? The angle between the current and magnetic field. In this case, current is up, magnetic field out of page, still 90. Okay, you see that once you find this force, the rest is just going to be kinematics and Newton's second law. Right. So you can try this, or if you want to do it using conservation of energy, which is my favorite law in physics 1. So you can just do this, right? Changing kinetic energy, there's no potential energy here, there's no electric potential energy here, right? So you can write it, this complete equation. So this guy may have different terms, right? Gravitational potential energy, elastic potential energy, and we also learn electric potential energy in this class. But there's nothing like that. There's no potential energy in this problem, right? First of all, it's not moving up or down. It's pretty much like that, right? It's moving in horizontal direction. So no gravitational potential energy, no elastic potential energy, and there's no electric field here, right, in this region. So this guy is going to become 0. Then you do this. Minus, right? This is the change in kinetic energy equals the work. Now this magnetic force is from the outside, right? It's from the magnetic field on this guy. So it's the external force on this moving bar. So that's when you do need the work done from the magnetic force, okay? And then how do you find the work done? So this guy is 0, right? And this guy, how do you find the magnetic force? The work done by magnetic force. Work has a definition. If you still remember that from physics 1. Force, displacement, cosine theta angle. Right? Again, what is the cosine theta angle? Well, it's just going to be the angle between the force and the displacement, because these two guys are the vectors, right? So it's going to be FB, which you're going to find. So you still need FB if you want to do conservation of energy, right? And then displacement is D, right, in this place, in this problem. Cosine theta is going to be the angle between the force and the displacement, okay? Force is in that way. Displacement is also in that way, so it's going to be cosine 0. Okay, this is also the simplest case for work. the force and displacement in the same direction, right? So now you see that you're going to get equation 1/2 mvf squared equals fb times d. Cosine 0 is 1, right? You just rewrite this equation, you will get the VF. So either way, okay, either way, but this is how you find the magnetic force, right? Using the current, the length, and magnetic field. So at the end, okay, pause the video, do the algebra yourself, see if you can get the right answer. You can either do kinematics or conservation of energy. So then you will get this. Okay? So this is the second part. Now the third part, the same question. Now let's add friction in this question. So again, if there's a friction when this guy moves, so the magnetic force is still on it, right? Because the magnetic force comes from the magnetic field. So that's just going to be a friction force opposite to its motion, right? So okay, again, converted to a problem in mechanics. Something's moving on a real surface. There's a pulling force with this number you're going to find, and there's also a kinetic friction on it, right? So how do you find kinetic friction? Mu k normal force, right? So that's the theory we learned for kinetic friction. So that's why the problem gives you the coefficient of friction, which is the mu k. It's 0.3, right? So mu k, it's going to be 0.3. Now in this case, the normal force is going to be equal to gravity. But it's not always, right? We have done many problems in physics 1. In this case, so because these are the only two forces in y direction. Okay? So now you see that you can use this to find the kinetic friction. Okay? And then once you find the kinetic friction, then you can still do the kinematic equations or conservation of energy. The only difference is this, right? If you decide to do this, you will have kinetic friction here. And then you find the acceleration, you plug it into this third kinematic equation. You will find the speed, right? Or if you do conservation of energy, this doesn't change, still no potential energy, but now the work is going to be this work plus the work done by kinetic friction. How do we find the kinetic work done by kinetic friction? Force, displacement, still d, right? Because the same displacement. Cosine theta. What is the angle between the force and the displacement for the kinetic friction? Kinetic friction is in that direction. Displacement in this direction. Cosine 180. So you will get a negative number here. Keep the negative sign, right? Use the definition, okay? You don't need to assign an actual negative sign. You don't need to remove an actual negative sign, okay? Just use the definition. You will get positive numbers, negative numbers, everything, okay? Then what you do is this, right? So this is just going to give you negative fk dk, right? You are still adding these two works. But this work is negative because of this cosine 180, right? And then you will find the speed, okay? You do all the algebra. This kinetic friction is going to be this number. So that's just only one extra term here. You will get this. Okay? So that's the only difference between this part and the previous part, okay? All right? I'm going to stop here for the third video.